say something. Hello? Works.
So let's start the morning session. The first speaker of this morning session is Jacques from University of Paris. The title of his talk is Divisibility towards the Anticyclotomic. It was a main conjecture for CM field part 2. Please start.
Okay. So we are studying the first divisibility, and for that, there are 3 ingredients and 2 arguments. So first ingredient has been studied. Now we study the second one. So we consider an integral ideal in R, prime to P. And we consider level groups, UN, matrices in GL2 of R hat, such that G is congruent to 1, 0, star 1, modulo n p to the m n. And for a given weight, we assume, so this weight is supposed to have the properties that all k sigmas are greater than 2, and k sigma is congruent to k tau modulo 2. So this means that it can be written as, so we introduce the parallel weight 1, so it's the sum of sigmas. Parallel weight 1, so k can be written as 2t plus something, which is positive inside Z of IF, all components positive, non-negative. So we fix an element in Z of IF, actually positive, such that n plus 2v is parallel, n plus 2v is parallel, so it's equal to, so mt, so some integer, m. And we put w to be t minus v, and we consider the space of cuspidal Hilbert modular forms of weight kw and level un. So these are the Hilbert cusp forms of level un, and automorphic, so automorphic factor determinant of G infinity to the minus W times G infinity Z to the K, where Z is an element of the Hilbert half space. Okay, and G infinity belongs to GL2 of F infinity plus acting on the Hilbert half space. Okay. Now we choose some, so we consider the Galois closure of F. We take some finite extension, which is finite but sufficiently big. And we have the ring of integers, OL. And now we modify, so we have the Hecke operators at all primes. If you take a prime Q, which does not divide n, we define the Hecke operator TQ as the double class UN by Q001 UN, double class acting on the space of cusp forms. But for, so let's say for Q dividing n, but for Q dividing P, which is prime to n, we modify these operators. So we modify them by as follows. So if you take, so Q divides P means that Q is one of my PIs of the first talk. So Q is one of these PIs. So we take we consider this this ideal. It becomes principal because we localized, and so we choose a uniformizer and a generator, and oh no, I'm sorry, no, that's not what I mean. It becomes, yeah, just a second. I take pi I inside pi, uniformizing parameter. Means valuation 1 at pi. Then I apply minus v to pi I, and this belongs to, or maybe plus v, this belongs to OLP. And then I divide, what is, I don't remember. So you see the operator TPI is nice, okay? It exists, it's nice, but it is divisible by some power of P, basically by the vth power of P. So you modify it by this, so by this division. So this happens in L, because you need, first of all, that this belongs to L. Does not belong a priori. It belongs to the closure, Galois closure, but so it belongs to L. And the role of L, the role of L is to be big enough so that the Hecker eigenvalues will be there later. For the moment, to define the operator, this is enough. To define this operator, this is enough to go to F Galois. But actually, we will need to have coefficients for the Hecker algebra in OL for L sufficiently big so that all the Hilbert modular forms which occur in this weight and level will have eigenvalues in L. So yeah, so you modify this operator by dividing eigenvalues of? Eigenvalues. Yes. They are related.
The eigenvalues all the time contain, not the Galois closure, but those be generated by the vth power of the
Yeah, you could be a little, well, yeah, you could.
You may have a Hilbert model form over F, which is defined over Q. Sure, that case V is the parallel way. So you apply Z to the V, it goes into the field generated by that.
I'm not looking for the best. You see, I consider the Galois closure because I want all the alpha sigma to be there. It's true that if you make a combination of these sigma, this belongs to a subfield of this, and that you can specify it. For instance, if you take this V, alpha V belongs to a subfield for all alphas in F, it will belong to a field, a Q of this, which may be Q, as you said. This field could be Q, if V is the norm, if V is parallel. But I am not looking for the smallest field. I am looking for, first of all, V is not necessarily parallel, and well, it does not matter for us. The field can be larger. There is a better field than this one, but that's not the problem. So anyway, we need to divide by this power to get some operator which is optimally integral, so that if you look at the part where, so you define the Hecker algebra as the HKW, it is a sub, so of level UN and with coefficients in OL inside the endomorphisms of the space SKW UN. So it's an OL algebra generated by the TQs for Q prime 2Pn and by the modified TPI, so 0 pi, for the PIs in SP of F. And so the point is that by this modification, if you take the largest subalgebra, so now maybe you take the p-adic completion of this for, so L is contained in QP bar by iota p, and you take the completion. So this is a finite O, maybe O algebra. Now, yeah, so OL falls in our O. At the beginning, I said there is a sufficiently big p-adic ring containing even a ZP unramified hat, okay? So we work with this ring. So now you have this finite O algebra. So this is an Inselian ring. So it's a product of local rings. And you take the product of the local rings in which these operators are invertible. This is what you call H nearly ordinary. But you see, if you didn't modify these TPI so that they are optimally integral, this could be 0. Because these operators are divisible by P. So if you look for the part on which they are invertible, that's 0. But by this modification, there is something interesting, which is called HKW. And now you take the projective limit over N, and that's the definition of H nearly ordinary. And the big theorem of Hida is that it does not depend on K and W. Okay, so there is no index here, no need.
Then it's still maximally invertible.
Okay.
Otherwise, you can't cover all the positive stuff.
Okay. Okay, so I remove positive. Everything remains there. Okay, so we have this algebra. And so as I said last time, it comes with an action of some torus. Because at each level, you have an action of diagonal matrices. Because you see, we took matrices congruent to 1 star 0 1. And so there is a group which normalizes this, namely, if you put star star, so gamma 0 if you like. So basically it corresponds to the torus so there is an action of the diagonal torus modulo np to the n. Okay, this torus normalizes this, so it acts on the space of modular forms. So it defines operators. So we put these operators in the Hecke algebra. I forgot. So you have these operators plus these so-called diamond operators, T of AB, for A, B in O modulo n P to the n cross, not O, R modulo n P to the n cross. So you have also these operators. So you have a map. So if you take the limit, you will have a map from the torus, which I call TP of n, which was, so as I said, there is an action of these operators, but among them you have the diagonal unit, like epsilon, epsilon, where epsilon is a global unit. And these act trivially for some obvious reason, okay, because of this kind of condition. These act trivially. So actually it's a torus, but it's not exactly the diagonal torus, which would be this. But it is this modulo the closure of so the diagonal embedding inside this torus of the global units. So this torus, as I said, has rank G plus 1 plus defect of Leopold. Okay, G plus G minus 1 minus S. So this torus has this rank, and so it maps to the invertible elements of the Hecke algebra, and therefore, if you consider the pro-p factor W0, so it is this times finite, and you consider the Iwasawa algebra O double bracket W0, you have a structure of lambda 0 algebra on this ring, coming from these operators, from these diamonds. Okay. G plus 1 plus S is the rank of the torus. Okay, so, and as I said, by a big theorem of Hida, this algebra is finite, torsion-free over this ring. Flat, yeah, not in the annals paper, but later you proved it's flat. Yeah, so. Okay, so it's finite flat for P at least 5. GL2. Yeah, and also the we will define CM Hida families, and they do have highly non-trivial Neben types. So it's not, yeah, very interesting Neben types. So you need GL2. So for us, N will be the norm from M to F of our auxiliary ideal times the discriminant from M to F, as you know in the old story of Hecke. So that will be our level. And we consider lambda a Hecke character of M, of conductor C P to some power, and the weight, so infinity type is eta, maybe eta iota infinity. So, and so eta can be written as a sum of eta sigma for all sigmas in IM, but also, as I said, it can be written as M0 sigma plus D times 1 minus C, where M0 is positive in our case. So that's what we assume, and D sigma is positive, or M0 is greater than 1, and D sigma is greater than 1 minus M0. So we consider such an infinity type. And we introduce MP to be M0 minus 1. And we introduce KP to be sum of eta sigma minus eta sigma C plus 1 sigma for sigma in sigma. And so we assume that eta sigma is bigger than eta sigma C. So we have NP, which is the sum, of course, of eta sigma minus eta sigma C minus 1, or sigma in sigma. We have VP, which is sum of eta sigma c sigma restricted to f for sigma in sigma. So if you introduce this data, you will have np plus 2 vp equal m0 minus 1 t, and therefore, so this is the mp, and therefore if you add 2, well, anyway, okay. So you have this, yeah, you call this mp, yeah, it's there. So it turns out now that for this data and the character lambda, so if we do the base change from GL1 over M to GL2 over F, we construct, given lambda, which is an automorphic form on GL1, we construct an automorphic form on GL2, which is a theta series, and which belongs to SKW UN O. And actually, it has an Ebentypus, but I don't write it now. So as you know, it is given by, it is a Hecker eigenform whose Hecker eigenvalues are something like lambda of big Q plus lambda of Q complex conjugate if Q splits, and Q is prime to N to N. And then it is 0 if Q is inert. And otherwise, it's lambda of only one Q if Q is ramified or split, but one, or split, but QC divides N, divides C. So you get this theta series. Now there is a modification, which I don't explain, to make it nearly ordinary. So this one will belong to the nearly ordinary part of SKW. Of course, it's a modification only at P. So it's again a cusp form of weight KW, but it is nearly ordinary. And its eigenvalues at the modified Hecker operators T0 pi is is a unit. We have units here. And so we can, so this gives rise to an algebra homomorphism from the Hecker algebra to O. And so this is what we call theta lambda star. Okay. It's an algebra homomorphism from the nearly ordinary Hecker algebra to O, associating to the Hecker operators these Hecker eigenvalues. And so so of course these lambdas have a p-adic avatar lambda hat, which is a character of the Galois group, so a character of delta C times W. And we fix the restriction to delta C to be psi. Okay, the character psi, which was given by the formula chi equal psi C over psi. Okay, we fix this this to be psi. And so when you vary lambda, you define a family. You define a family of the nearly ordinary Hecker algebra with values in, if you think a little, in lambda. Because you see, you can interpret these quantities as, so this, instead of writing lambda of Q plus lambda of QC, you could write Q plus QC and consider this as an element. Maybe you replace this by Frobenius Q as an element of O double bracket G infinity of C. Okay, and similarly, all these elements could be viewed there. And then you could consider that you specialize by lambda hat these elements. Okay, so you could interpolate these quantities by these kind of things. And so that's how you could define directly, for instance, TQ, if Q splits, would map to Q plus QC, except that, of course, you have to project plus the times psi of, because it's only the projection on lambdas on this one. Okay, so you put maybe a bracket, and here you put a psi of Q, and here a bracket, and or maybe a bracket outside. Bracket outside plus a bracket outside times psi of Q times psi of QC. Okay, so that would be the definition of the Hida family. And if you look at the formulas, especially about the Nebentypes, you can prove that this is a lambda zero algebra homomorphism, where the map here is induced by class field theory. So there is a natural embedding of, not embedding actually, actually embedding from W0 to W, which comes from a map which is not an embedding from this to G infinity of C coming from class field theory. So, so you have really a Hida family. And so that's theta psi dual. And this ring is a UFD. So you can define an element H psi inside lambda up to unit. Okay. Congruence power series associated to this family. Okay, the congruence power series up to unit is an element of lambda associated to this family. So we have defined it now. If you have a, yeah.
Then the lambda
Okay, so the third ingredient now, they disappear. No, they didn't disappear. So Rankin-Zellberg p-adic L. So we focus on yeah, so it's nice to see the picture like that. So there is a specialization coming from H. So there is this picture to keep in mind. H nearly ordinary goes to lambda. There is this family. Then there is the specialization going to H, K, W, U, let's say U1 or well, UN, maybe it doesn't matter so much. UN, O, nearly ordinary. So it's some, it's a quotient by some ring P and V, by some ideal. This is an ideal inside spectrum of lambda 0, which I will write down. It's called an arithmetic prime. I will write this prime. And here you have also a specialization by quotienting by some prime ideal of spec lambda. This prime is above this prime by the map from lambda 0 to lambda. You have P, and here you have P and V. Okay, and here you have what I call the theta lambda star. And what are these? And this diagram commutes. This is surjective, and the kernel is exactly the multiples of this in this ring. And so, what is the so what is P? P is induced by the map W goes to O cross. If you have an element W, you send it to W to the eta. It makes sense if you consider that this is contained. Well, okay. I'm sorry, but I don't want to. So, and W0 to O cross, so this is the PNV. So it will be a prime ideal, but first it's a group homomorphism, then you linearize and then you take the kernel, okay? So I define here a group homomorphism, then it becomes algebra homomorphism by passing to the completed group algebra, then you take the kernel. And so here the map, so if you remember, these are elements A, B, and so you send AB to A to the N, AB to the V. N is, okay, these are elements of Z of IF. N and V are elements of Z of IF. So this is the specialization in weight KW. And this one is the specialization in weight eta for GL1. This is a specialization for GL1. This is a specialization for GL2. Okay, and that commutes. And so, now we fix another character of delta C hat different from psi. We consider, but same conductor, and we consider theta phi hat and theta psi hat. So these are two Hida families, and when you have two Hida families, you can define a Rankin-Zellberg p-adic L function associated to these families. So I just recall what is the Rankin-Zellberg product. So if you have two classical modular forms, here I take classical, they could be Hilbert, but I take the case F equal Q for a second. So I define, I take two classical modular forms. One is on S gamma 0 n epsilon, and the other one is in S L gamma 0 n eta, and I assume K strictly bigger than L. Then one can define the Rankin-Zellberg product. So it's so this is the primitive one. Okay, the primitive one is defined as the product of the Euler factors for, if you take the Galois representation of rho F tensor rho G, and you take the motivic L function. So this is the perfect L function, but usually you don't get it on the nose. You get something in primitive. So this one is the primitive. This is the perfect one. But usually in the calculations, that's not what you get. So you will get something which is correct for the Euler factors outside N. And at N, it's usually not exactly the correct Euler factors that you get. So there is extra work. But so that's the perfect one, okay? Euler factors for this representation. And so it admits analytic continuation plus functional equation of the type S goes to L plus K minus 1 minus S. And the critical values are J between L and K minus 1. So the center of the critical strip is L plus K minus 1 over 2. And you have the fundamental formula of Shimura, I think, which relates the critical values to a Peterson product of two modular forms of weight K. So you have this fundamental formula, D of L plus M F G. So M is an integer between 0 and K minus L. Actually, we consider for the moment as you can see, so there is the critical strip from L to K minus 1. You have the middle, which is K plus L minus 1 over 2. And here you have K plus L, or K, sorry, K, is it correct? where is this? K plus L minus 1 over 2. So you have the integer just before, and that corresponds to L plus this. So what is this? This is K plus L over 2. K plus L over 2 and K plus L over 2 plus 1. Well, of course, they could coincide depending. Well, yeah, it depends on the parity, but okay. Yeah, so we are on the left-hand side of the critical strip. And so the formula is that it's up to some explicit factor. It is given by Peterson product, the mass Shimura differential operator to the power m applied to the standard Eisenstein series of weight k minus L minus 2m. This differential operator increases the weight by 2 for each time, so 2m. So this is the Peterson product on gamma 0m.
G times delta then upright.
Yeah.
Then remove the W.
Oh, okay. Okay, okay. Yeah, okay, yeah. Oh, it's not Shimura? Okay, all right. Okay, so this is weight K, this is weight L plus K minus L, so weight K. And so, yeah, okay, so this is a modification by Hida of previous formula of Shimura. So this means that if you divide by the Peterson product of the primitive form associated to F, so you will have this divided by the primitive, so by the Peterson product of the primitive form associated to F, you get some nice algebraic number, and you can write it absolutely explicitly. And because of that, now, as I said, when you want to construct a p-adic object, you have to imitate the Archimedean construction p-adically. So this formula allows you to interpret p-adically this thing and vary it. So by varying it, you get some p-adic L function. So for us, we will take F to be the theta of lambdas pertaining to theta psi, and here the theta, let's say, of nu pertaining to theta phi. Okay, we take for G. Okay, and so you get something which we call psi phi, and it has two variables actually, two packet of variables. So it will be in lambda tensor lambda, except that it has a denominator, and this denominator is precisely h psi, because h psi is related to this by the so-called adjoint L function special value. Basically, that's a formula, I think, due to Hida. L adjoint 0, so 0 means SL2, okay? Adjoint 0, 1 is explicitly the Peterson product. That's Shimura. Okay, well, all right. Okay, so that's Shimura. Yeah, so, and this is related to H psi. Well, it's a long story. Anyway, so you define an element in here which interpolates these values for these series varying in these families. And so I can write just a vague formula of interpolation. if you take two primes P and Q as I defined before, okay, like this, so one will be W to the eta, the other one will be W to the nu. Yeah, nu is the weight. So maybe this, I shouldn't call nu here, I should call it lambda Q. I don't know how I should call it. Yeah, no, nu Q, and this one lambda P. And so then, so I take two primes, so one will give rise to the lambda P, and this will give rise to the nu Qs belonging to the respective families. Then D psi phi specialized at these primes is up to something very explicit, equal to D. This is the weight of Q, theta lambda P, theta nu Q, divided by theta lambda P, theta lambda P, which, as I said, is related to an adjoint L function. Okay, so that's, so, yeah, so very vaguely, that's what you get. So you have the three ingredients, and so now we start the proof. Very, very sketchy. This means we start the second talk. Capital. Yeah, so this one is the p-adic L function. So as I said, you have, so D, I defined it. This one I defined, okay? This is the motivic L function associated to F tensor G, okay? So the special values happen to be equal to this Peterson product. And because of this formula, you are able to interpolate these things when M varies, F varies, and G varies in Hida families. So for us, we let F vary in the family theta psi, and G vary in the family theta phi. So this is the variation. This is the elements of the family, if you like. And so there is an object like that. That's the theorem of Hida. This is the p-adic Rankin-Zellberg L function, such that, so it has a denominator. It's not integral, but anyway, when you specialize to P and Q, which are not zeros of course, of H psi, you get this value.
So here you evaluate that.
KQ is the L. KQ is the L. Is the smallest one. KQ. KQ is the L. So F was weight K, G was weight L. So that's the L. Actually, you could do better, of course. You could also, you could also evaluate at shifts of that. But we need only this one. We need only this one. Which means that we don't need the mass Shimura operator, because M is 0, which is allowed, of course. M could be 0. Well, yeah. No, what? Yeah, M could be 0. You would have the Eisenstein series of weight K minus L and G of weight L, and yeah. Okay, so now the first part is the relation between D psi phi and cats L. And so so of course, for us it will be important to write it as something integral divided by H psi, because it can be written like that. So anyway, the lemma is that DL F G complex conjugate is equal, so again, up to Euler factors at primes dividing, well, or maybe okay if I define this to be the primitive. If it is primitive, then this is equal to L 0 rho F tensor rho G dual. You take the motivic L function for this motive and you evaluate at 0. So that's easy. Don't prove this lemma. But if you have this lemma, you have the consequence that if you take d of S plus, if you take d of KQ theta lambda P and theta nu QC, complex conjugate. Yeah, maybe there is a complex conjugate somewhere. Here? Yeah.
That's the sign. The middle. Actually, my formula. D L plus M. You have W.
D?
You have WN there.
Yeah.
WN applied G is G complex.
G complex conjugate. Yeah. So that's why. Yeah. So here it's complex conjugate. And so you need the complex conjugate. So you have this complex conjugate and you get L of L, if you are careful, you will get L1 of this representation. So that will be induced from GM to GF of lambda P, and the other one is induced from GM to GF of nu Q to the minus 1. And this is how you relate. Yeah, just a second, because it is LS plus L minus 1. I take 1, so because it's not 0, because it is 1. S plus L. This is equal to this. That's true. This is equal to this. Therefore, this is equal to this. And now you see the relation between the Rankine-Zellberg L function and the Katz L, because, or the Hecke L for the moment, because you have a very simple formula of group theory, namely that this tensor product of induced representations can be written as the sum of two induced representations. Oh, I didn't write the formula. So I just wrote the, so yeah, so this is, of course, this is an Euler product involving Euler factors over F. This is same thing, of course, involving Euler factors over F. But if you calculate this, you find that this is the product of L functions involving Euler factors over M at 1, lambda T nu Q minus 1, and Lm 1, lambda P nu Q to the minus C. So basically, that's the key point in some sense, because you pass from Rankine-Zellberg of two modular forms to two Hecke L functions. And so they will be interpolated. So now you use the functional equation, and you can write this as L0 lambda P minus, well, it's not functional equation actually, it's just for the moment, yeah, it's not the functional equation. It's just that this can be written as lambda P minus 1 nu Q star. You remember star was and L, but yeah, it's not the functional equation, but what you get is star object. And similarly, so this is one thing. And for this one, you have a similar observation. This is related to the adjoint of what? Of the induced representation from Gm to Gf of lambda p at 1. And if you compute this, you will find that it is the L function of the quadratic character of m over f. So alpha is the quadratic character of m over f times the L value of the character lambda p. So let's just a second. Lambda p divided by lambda p to the C1. In other words, it becomes anticyclotomic. So this is the place where you get something anticyclotomic. So this is just a simple group theory. Okay, the adjoint of the induced is not trivial. It's a quadratic character plus the induced of this. But so this was over f. Okay, so I go to m. So this is still over f, but this is over m. So here you see the anticyclotomy appearing, and here you see Katz L appearing because you will interpolate these things, and they will give rise to Katz L. So now it's a very long and delicate, not delicate, I mean, long calculation, which proves that by interpolating these equalities, you prove it's a very careful inspection, and it works so well that it's a kind of a miracle, that finally you get the theorem that phi applied to P and Q divided by H psi of P happens to be some unit times some Euler factors, which are quite explicit, at C, quite explicit, times, unfortunately, L1 star, L2 star. So these are Katz p-adic L functions, but on the negative critical side, okay? You had two types. You had L, which was associated to mu, and you had L star, which was associated to mu star. And in the calculations, what appears is this one, okay? So L star appears. So that's the way it is. So divided by the anticyclotomic L function, but star again at P. And so now you need to use the functional equation. Sorry, which one? Yeah, well, after careful examination, you get this. Yeah, well, I guess it is up. Yeah, but it will be some constant, no? Yeah, class number, but we will neglect that because we will work in lambda of 1 over P. You need, but I didn't do that. Yeah, you will have to. So I should write something here. Okay, this I didn't write because I work in this setting. Okay, so the constants are okay. Yeah, so that you get. It's a careful examination. Basically, it's here. It's here plus functional equation. Now you will use the functional equation. Sorry. Now you use the functional equation. And so now you can, by functional equation, you have U, which is a unit, times another unit, V. You will have this psi, and you will have L1, L2 divided by L anticyclotomic star, L anticyclotomic star. And you see, Okay, now I remove the P and Q because it's an exact formula. So if you can interpolate, so if you have two series which have the same values, exactly the same values, they are equal, okay, by Weierstrass preparation theorem. And so psi, it's an interpolation of Euler factors because there are, you see, here there are some Euler factors. I didn't write them, but they can be interpolated.
These are the bad Euler factors.
Yeah.
There is the motivical function and there is more.
Well, yeah, what you get in this, when you prove this, you don't get if you want to get the motivic, you have to modify some Euler factors. Yeah. Because I defined it motivically, but that's not what appears in the formula. So you have to modify the Euler factors at primes dividing n. But what you get is this. These are units. This is, I don't know whether it's a unit, but no, maybe not. Maybe not, but what you want to prove now, you remember what you want to prove? You want to prove that this divides this. You want to prove that L anticyclotomic, so there is no star anymore. You apply, because you apply the functional equation, okay? So L anticyclotomic divides H psi. You want to prove this, and so you basically what remains to be proven is that let me see. If you have a prime which occurs in LA chi, yeah, so the branch will be chi because, as I said, it's anticyclotomic. Lambda p is in the branch psi. Therefore, this is in the branch chi. So if you take a prime here, you will need to prove that it is prime to this, this, and this. Okay. Therefore, if you have some power of this prime if you have a power of this prime which divides this, it will divide this. Chi, yeah, chi, because we have to interpolate these things, but these things belong to the chi branch. Okay, so it's the. No, I don't think so. What? Well, in our paper, we use the functional equation. No, also in denominator, because that's what we want. We want to prove. You see, if I get, so you have phi L A chi equal, you need this L1, L2, and H psi. So these are units. You want to prove that this is the one we want to study, is prime to this. Therefore, it divides H psi. That's the one we want. And that's the one we mentioned in our paper. Well, okay, it's up to a unit. Yeah, okay, so this unit, I didn't say what it is, but you can absorb it as the unit involved in the functional equation here, functional equation here, and functional equation there. Yeah, well, of course, I forget about U and V. Yeah, these are units. So what I want to prove is that if R to the K divides this, then this R does not occur here. Therefore, R to the K divides that. And how to prove this? You have to look at the shape of this. So this depends on really the two variables, psi, P and Q, okay? You have really these two variables. But there you have only, but the other one, H, this one has only one variable, okay? Only the variable P. So you have to see how the variable works, because actually it will be the cat L of something. And basically you can, if you consider cat L as a function of W1 and W2. No, a function of W, okay? W belonging to W. So L1 is a function depending on two W's, W1 and W2, and actually it is the cat L for phi psi minus 1 of W minus 1 W2. That's the cat L which happens really. And similarly for the other one, you will have something with C maybe. And now what happens is that if R occurs in L1, for instance, if R occurs in L1 of W1, W2, here this depends only in W1, sorry, R. What you do is to consider a zero of L1, so what a zero of this anticyclotomic L, of R, a zero of R. So the notion of zero requires that this is not the prime P, okay? The prime P has no zero, but any other height 1 prime, because those are height 1 primes, any other height 1 prime is given by some sort of distinguished polynomial in some sense, so it has zeros somewhere. And so if you have a zero of R, you can approximate it by oh, just a second. We choose a sequence Tian. So as I said, this is an element of lambda. So it's basically a prime of height 1. But now we consider primes of dimension 1. Zeros are primes of dimension 1, okay? Which means that these are evaluations to O, which give so of dimension 1. Exactly. So that's completely different. So this is height 1. This is dimension 1. The zeros are dimension 1. The zeros are dimension, so they are not at all like that, but they are zeros, okay? Correspond to sending W1 to something. So it's a dimension 1 prime. So we consider a sequence of dimension 1 primes which go to a zero, I don't know, a zero of R. Then, of course, this when you specialize to this prime, goes to 0. So if you take R of, maybe I write Pn of W1, this is divisible by a very high power of m when n grows. But on the other hand, if you look at this, when you specialize W1 to anything, there is a mu invariant of this cat L, and if you specialize W1 to anything, the mu invariant does not change. Similarly for L2 and similarly for psi, which is absolutely explicit, okay? You just So what happens is that a higher and higher power of P will divide this, this element of lambda, which has a fixed mu invariant. That's a contradiction. So that's the argument. And so for L1, for L2, and for psi. And so it is impossible to have a common factor R in anticyclotomic L and in these primes. So it divides H psi. So that's the argument for sketch of argument for proving the one divisibility. And now for the second divisibility, it's completely another story. And there we don't need to invert P, actually. It is deformation theory. So completely another world. I have 15 minutes. 10 minutes. Yeah. 15, yeah, well, okay, thank you. Yeah, so for the second part, yeah, for the second part, second divisibility, actually we will do that. So we want to prove something like H psi divides, let's say Z of F anticyclotomic chi sigma C. And so we will do that for each height 1 prime dividing H psi. So we fix a prime P height 1. And we try to prove that so if P to the K divides this in lambda, then P to the K divides that. And so we have the universal deformation of the character psi. So it's a character of G infinity C with values in lambda, sending, so you remember this decomposes as delta C times W, and so we send to psi of delta times W, which is an element of the group algebra, completed group algebra. So this is the universal deformation of psi, capital psi. And so we assume three assumptions, A1, A2, and A3. So actually, there are some assumptions to prove the second divisibility. So as I said, all the primes in C split from F to M, so are degree 1, relative degree 1. So this means that the I, if you remember, C was F, FC, and I, so this is assumed to be 1. And so the second is that for any P in sigma, well, in P, the restriction of psi at the decomposition group is non-trivial. And if you denote by psi star the restriction of psi to Galois of M bar restricted to M of square root minus 1 P minus 1 P star. You know, sorry, P, well, P. This is the number P star in White's work. This is non-trivial. So we, sorry? P minus 1 over 2, yes. That's what I wrote. Okay, and so what we'll do is to use deformation of the representation with values in GL2 lambda. So we are allowing very big rings, okay? So this is maybe one of the reasons why A3 is psi. Or is a chi? Okay, so yeah, I copied from your paper, but your paper has different notation from, yeah, I'm sorry, okay. Okay. So, and this is a chi also, yeah. Okay. So we consider the induction from GM to GF of psi, which is a representation of a Galois group pi to GL2 of lambda. And so pi is the Galois group of L prime over F, and L prime is the maximal P ramified extension of the class of the ray class field MC. This is the ray class field of M of conductor C. So unfortunately, as usual, we don't know that pi is topologically finitely generated. Okay. But maybe it is, but may not be finitely topologically generated. But as usual, we know that its Fratini quotient pi divided by pi p is finite by Kummer theory. And so we consider, so this is a representation. So the representation we really want to deform is the residual representation of this, but modulo capital P. You see, we focus only on this prime P that we fixed. We fixed this prime here. What we want to prove is that this implies that P to the K divides this one. So we consider maybe we call it residual. The residual representation is rho hat modulo P. But of course, the ring lambda modulo P is rather huge. Okay? But still, it is a Noetherian local ring. So what do we know about the representation rho hat? We know the determinant. Determinant of rho hat is no, you asked me to mention these assumptions because you will use them. So I mentioned them, but I don't use them. I mentioned that because you will use them. That you asked me. Yeah, I don't use a distinguishedness. What we know, of course, is that, yeah, so maybe I assume that chi is not 1 because I need that psi is not psi. But even psi could be psi c because you see the universal deformation psi is never equal to its conjugate. Okay, and even modulo P, modulo capital P. So distinguishedness is not assumed. And so, yeah, determinant is psi c times alpha. Alpha is the character. Whatever it means. Well, it's the usual Nebentypus of some theta lift. Okay. So, and so we have psi anticyclotomic, which is defined to be psi c minus 1. Maybe it should be a chi, but big chi is not good. So, and so we will, so now we need to consider the completion, the p-adic completion of lambda. Okay. Which is, so the good point is that it is a complete DVR. So that will be our DVR. So its residue field is the field of fraction of this ring. So unfortunately, it's not so nice. It's the field of fraction of this. But it contains lambda over P. And there will be some topological subtlety because these fields are not so nice. And so our Artinian rings over this kind of rings are not so nice. We will always assume that they contain a lattice which is compact, like this, coming from, which is finitely generated over lambda. There is some topological subtlety in this approach. So I will be now very sketchy because. So we need, so anyway, so what is the key idea? The key idea is to relate congruences, and Selmer group. So maybe I will be very sketchy. Okay. We will define a problem of deformations over lambda p cross, lambda p hat. So we consider the category of lambda p hat Artinian algebras to the category of sets. So when you have such with residue field, this field over there, A, you consider the representations from pi to GL2 of A, such that rho modulo maximal ideal of A is rho p bar. It will be nearly ordinary, but so of course that's kind of thing we need. But there is a topological condition. So there exists a lattice in A square, which is, so this means a lambda submodule, which is finitely generated over lambda, such that lambda p hat of L is A square, and stable by Galois, and such that rho viewed into GL of L is continuous in the usual sense for the lambda-adic topology. Okay? We consider, so nearly ordinary is that if you restrict for any V dividing P in F, if you restrict rho to the decomposition group, it falls in a Borel up to conjugation. Up to conjugation, it falls in the Borel, and on the diagonal, you will have characters alpha and delta, and they are congruent respectively to I don't remember if it is psi c, yeah, psi c, and well, alpha is certainly, well, I don't know, I wrote psi c, okay. Anyway, congruent to psi modulo p, up to modulo maximal, and delta is congruent to psi c. Okay, that's the near ordinarity and continuity. And we fix the determinant. And determinant is the same. Determinant of rho is the determinant of rho hat. Okay, rho hat takes values in GL2 of lambda, hence GL2 of lambda p hat, hence GL2 of A, and we assume there is no deformation of the determinant. Okay, so it turns out that this problem is pro-representable. So you will have some universal lambda p hat algebra, which pro-represent this problem, and there is a deformation to so is it enough to do to lambda p? Maybe, I don't remember. So maybe call it R nearly ordinary, and yeah, so, and there is, so if we consider H nearly ordinary, there is a modular representation. constructed by Hida, actually, to H nearly ordinary, provided, so maybe you have to localize a little bit. Yeah, so there is a nearly ordinary deformation. So maybe it's not perfectly correct. You need to localize, but we will localize. So rho Hida, maybe. Nearly ordinary deformation of rho hat. And so I am very sketchy, okay? So we localize, we consider, we localize at P. So this is the local component containing the family theta, psi. See, well, yeah, well, because it's a local component. You see, first of all, you tensor by lambda p, then you decompose, and then you take the local component. So that's why I denote it like this. So h of p, or h nearly ordinary, the local component. And so by the universal property of this ring, you have a map from h nearly ordinary of p. And this is surjective by abstract nonsense, because here this is generated by Hecke operators, and Hecke operators are traces of Frobenius, which belong to here. So this is surjective. And what you do now is that it's completely formal, it belongs to Mazur's deformation theory, that if you take omega r nearly ordinary tensor some module, which is a lambda p module, tensor over lambda p hat, you will get the dual of h1 of pi nearly ordinary with coefficients in add 0 of no, so yeah, so here it's r nearly ordinary, and the map, so W is a lambda p hat module. It's a lambda p hat module, and you view lambda p hat as a R nearly ordinary module by the representation rho hat. Okay, rho hat creates, actually it creates here a representation, he creates a map here to lambda p hat. This was basically theta psi. And this is the map I am talking about. So W will be a module over lambda p cross. Then this is H1 nearly ordinary, H0 rho hat, if you like, tensor W. So that's completely formal. That's Mazur's dual, maybe a dual. Yeah, well, okay, so you have this. But on the other hand, you have this surjection. So this gives rise to a surjective map from this dual to the same, replacing R nearly ordinary by H nearly ordinary. And what you get is some easy lemma. Okay? There is an easy lemma telling you that this module, so if you have, so maybe let me state this because this is useful, maybe more useful than all this business. If you have a diagram like this, R goes to O over O, finite, so R is finite flat. R is finite flat. This is algebra homomorphism. O is a DVR. And you introduce C1 of lambda to be omega R over O tensor O over, so over R by lambda. And you consider C0 of lambda, which is O modulo lambda of the annihilator of kernel of lambda. So this is the congruence module that I defined. Okay, this is exactly the congruence module that I defined. This is called the higher congruence module, so it is more subtle. But if what you always have is that the fitting ideal of C0 divides the fitting ideal of C1. And actually, equality holds when the ring R is a locally complete intersection. But anyway, so we don't need that. We need only this general fact, this abstract nonsense. So for us, this will be, so for us, O is lambda P hat. This fitting ideal is H psi. Okay? And this one is the fitting ideal of this module. Well, yeah, well, you can, yeah, let's say of this module, and now you have to relate this module to our Galois module. And actually, it's a Hochschild-Serre exact sequence, which tells you that this is a priori called the Selmer group, but this is an induced representation. So by Shapiro's lemma, by going to M and even to M CP infinity, actually, you will see that this is just the Pontryagin dual of the Galois group we were studying. So it's a little long story, but since I have no time. So basically, this Selmer group, this nearly ordinary Selmer group, because it comes from a CM representation, happens to be the Pontryagin dual, so double Pontryagin dual, if you like, the Pontryagin dual of the Galois group. So you will get home, because, yeah, I forgot to say what I take for W. I take I take the field of fraction of lambda P hat divided by lambda P hat in order to have double Pontryagin duality. I take this as W. So you will get home of our Galois group to this. But then you take again the Pontryagin dual and you get the Galois group. And so the fitting ideal of the Galois group, which is, as we know, if you take the envelope in height 1, this will give rise to F sigma anticyclotomic chi. Okay, and so you get H psi divides F psi. So it's an interpretation of Selmer as Galois, which gives the answer. And there is this V, but this V, when you do the interpretation of this as Galois, you will see this, this V occurring. Okay, this quasi-section occurs when you interpret the Selmer group as a Galois group, as our Galois group. Yeah, so I stop here.
Are there any questions or comments?
The aim of the lecture was to sketch the aim. Can you hear me? So I wanted to present 3 ingredients and 2 arguments. This was the proof of first divisibility. So I finished that about 40 minutes from the beginning. And then I started the second part, which has nothing to do with that. So this is the plan for the proof of the first divisibility, which was relation between Katz p-adic and congruence power series. So there is a Katz p-adic L function, and there is a congruence power series. So to prove this, you need 3 ingredients and 2 arguments, and that was the first part of the talk. The second part of the talk was another divisibility. This was divisibility 1. And divisibility 2 was H psi divide the characteristic power series of the anticyclotomic Galois module, which was in the picture in the first talk. That was the one involving instead of going straight to the ray class fields and considering the maximal sigma ramified, you consider the anticyclotomic extension of M, and then you consider the maximal sigma ramified P abelian extension. So we were studying this Galois group. It has a characteristic power series, which was called F anticyclotomic chi, for chi, a character of delta anticyclotomic C. So, and here you have W minus, which is the anticyclotomic Galois group. So this is ZP to the G. So we were studying this module as a module over this completed group algebra, and it has a characteristic power series. The ultimate goal of the talks was to prove that the anticyclotomic p-adic L function of Katz divides the characteristic power series of the anticyclotomic Galois module. So the anticyclotomic Galois module is this one, okay? And I say that it happens to be related to this Selmer group, and this Selmer group is related to the congruence power series because of this lemma. So here, congruence power series, here, Selmer group, well, fitting ideal of Selmer, but fitting ideal of Selmer happens to be fitting ideal of our Galois group. So that's the goal of the talk. And in here, you don't need to invert P. Everything fits well. So there is this quotient of class numbers that Haruzo was mentioning. It happens in this calculation. When you want to relate Selmer to Galois, you will have this factor extra. So what we prove is exactly here that this divides HM over H F in lambda. There is no need to invert P. Here, there is need to invert P in our proof. This will be solved by Haruzo in his lectures. So there is a problem here. Here, there is no problem, actually. It's on the nose that Selmer happens to be some class group plus Galois. So that was the goal of the talks. Thank you for asking. Yeah, when a classical modular form varies in a family, well, you cannot interpolate the Peterson product because Peterson products are transcendental by periods. Yeah, so actually, there is a formula due to Hida telling you that Peterson product divided by the Manin periods are actually the congruence numbers, is the congruence number of F. And so on the other hand, by Shimura's formula, this is L adjoint 1 divided by these periods. There is maybe a power of pi, omega F plus, omega F minus. So yeah, you can interpolate these things, and you can therefore interpolate these things. So you can interpolate these things to, yeah, of course. Yeah, the thing which interpolates these things is H of psi. Well, H of the family. Here for a CM family, but for yeah. But it's only a value at 1. Yeah.
Other questions? So let's thank the speakers again. We change the schedule of the next talk. Next talk start from 11:40.